going?
We're recording.
All right. Hi, welcome to yet another graduate student seminar. This time we have me again talking about the ends of groups. So last time we talked about ends of spaces, and this is a general or specific specialization, hence the absence of Bryce, of the ends of spaces. So yeah, without much further ado, we'll hand it to the speaker. So ends of groups. First we have to define the ends of spaces in an equivalent but different way, specific to geodesic metric spaces. Because last time we looked at the ends of just generalized continua. But in order to talk about ends of groups, we have to define it more conveniently than we did last time. So to remind ourselves of our previous definition, once again, same subspace of R2. I will probably draw more ends here. Another end. So we want the space obviously to have like 4 ends.
We're having the same issue again. Do you have a different marker?
Yeah. Grace to the rescue?
Maybe. Grace to the rescue? Yeah.
Thank you. Oh, wow.
Yeah, all right.
Okay, the blacker the marker, the sweeter the talk. So we have, subspace of R2. The way we defined it last time, because we were working with the generalized continuum, we didn't have any like nice properties like a geodesic metric space, so we had to basically use the analogy of like, Abril, Bryce, and I choosing to kind of run away from a flash flood, and so you have like, after a certain amount of time, you have like all of this interior of this space flooded, so you have to basically choose a place to go. So you could choose to go here or here or here, and then after a little bit more time, more of the space gets flooded. You have to once again choose to continue to move on. And you'll get to a bit of a crossroads at this point when this whole place gets flooded. So if you were here, you have to choose whether you want to go into this end or into that end. That's how you kind of define the ends. We used, for the areas that are flooded, we used nested sequences of compact sets that cover the entire space. And we used sequences of connected components, and again, nested sequences of connected components to define the actual ends. But now that we're working with geodesic metric spaces, we have way cooler properties that we can use. We don't have to go through any of these shenanigans. One obvious thing is that obviously geodesic metric spaces are path connected, right? So what is something that we always wanted to say in our definition, but we couldn't? Now we can say it.
What's the smallest path distance?
Right, we can actually, like, what are we doing? What is Abril, Bryce, and I doing when we travel to different ends? We're taking different paths, right? We couldn't say that last time, but now we can actually say their paths. So if I write down the definition here, maybe I'll start with geodesic. These are simple definitions, so I'll probably just run them fast. Geodesic is a function into your space X such that F is an isometric embedding. And the geodesic space is just a space X, space X, such that, again, I'm just rushing through these because these are really basic definitions, such that for all any 2 points in your space, you have a geodesic that connects them. There exists a geodesic from X to X prime. So connects them just means, at 0 it's at X, at L it's at X prime. This is, hold on. So let's see. So now we know what space we're working with. Obviously, space is a metric. How are we going to define this path to infinity? Let's see. Well, one thing that Abril pointed out last time is that you can't have these paths kind of, they have to go into infinity so that you can define an end. You can't have these paths kind of like squiggle around, in the same sort of bounded set the whole time. So that means, obviously, at some point in time, you want these rays, these paths, to basically get out of a bounded set and never revisit it again. So it keeps going further and further. So a proper ray is a ray such, and ray is, well, it's a function, from 0 to infinity into your space. That's a continuous function. Into your space such that bounded, such that the pre-image bounded set is bounded. So that's the second part is what makes it a proper array.
So sorry, is your geometric space, so is it
Geodesic.
Geodesic space, is it going to be a Hahnian manifold with a metric on it, or is it just a metric space?
It's just a metric space.
Okay.
Yeah. Yeah, well, with this property.
Okay.
Things are connected by geodesics. So this second property guarantees what we said. So again, pick a bounded set. So if I pick this bounded set right here, my array, if it keeps revisiting this bounded set an infinite number of times, this property fails, right? The preimage isn't bounded. So it has to kind of leave that bounded set at some point and then never revisit it again. You draw a bigger bounded set, do the same thing. And so it has to run off into infinity somehow. So that's how we get our proper arrays. Let's see, what's our next one? Well, again, like last time, we're just doing the same thing that we did last time, except we're trying to make it way more convenient for us to work with instead of using nested sequence stuff. So just like last time, we don't want like this path, or sorry, I'll draw it here. We don't want this path to denote a different end than this path, because they're supposed to go off into the same infinity, right? So we have to obviously define an equivalence relation on these paths. So on these proper arrays. So first, let's define that. So our ends. Let's say that two proper arrays are equivalent if and only if for all bounded sets B, there exists a T, so a time basically, that would be compactified, sorry. A time such that the image so the rays after that time are path connected. So they're in the same path connected component. Does that make sense? Okay. So this guarantees that these two rays will end up meaning the same end, because no matter how large I draw my bounded set, after a certain time, they're both going to be path connected. So now we're finally ready to define our end space. And that's easy to do. Now we have our equivalence relationship, so then the end space of X is just equal to the set of, maybe I should write, okay, I'll do this.
Sorry, so I don't know, so what are the connected components again in this empty space?
The what?
What are the connected components?
The connected component. Oh, sorry. Yes. My bad. Path connected. Like if you, so it's if you take the set difference, if you remove the bounded set, yes, thank you. If you remove the bounded set, then they're in the same path connected component. I need to figure out where to write the rest of this. I guess I'll just use this part. So then let's define a little n, so little e, end of array, a proper array, is just equal to the equivalence class of that array. So this is your ends. And then formally we'll just say that the ends of x, the n space of x, is the set of all the equivalence classes, such that gamma is a proper array. So yeah, this just now it's way easier, right? Like we didn't have to deal with anything super abstract. Just set an equivalence class on your arrays, and then each equivalence class will give you a different end. Okay, any questions? Okay, so you can see it's intuitively the reason I did that whole shenanigan with the flushing out thing, the flood, everything, is because I want you to at least see intuitively how the two definitions are the same. They are, you can prove that they're equivalent, but also it's easy to see that they are. I think I can erase this probably. Yeah. All right. So we defined our ends. What next? Well, so okay, we have our ends. We need to figure out how to. Last time we like compactified the space using the ends. This time we don't really have to do that. But what we do have to do is we have to define another set of things called quasi-ends. I went back and forth during the preparation for this talk on whether I should like talk about this, whether like very in detail. I think I've decided now that I will. So yeah, well before that, I guess I'll define the topology on the end space. So you have your end space. The topology on your end space is defined as follows. So what we do is we take a sequence of ends. We'll do this. And we'll say it converges to some n if for all bounded sets B, there exists a sequence of times. I'm just going to refer to them as times because that's basically what they are. Sequence of times such that for sufficiently large, and I'll give the geometric interpretation of this, and so it's easier to digest. For sufficiently large n, the n space, n represented, or sorry, for sufficiently large n, you have that the array from Tn to infinity, and yeah, okay, the array that you want it to converge to from Tn to infinity are path connected in X mod B. So what does this mean geometrically? So we're trying to define some sort of a convergence sequence. Like we're trying to say these ends converge to some n, right? And you'll see why we're doing this pretty soon. But let's do an example. So let's say there's a space. See, that's an end in your space. And then you have the sequence of ends that kind of do this. Okay, so you have gamma 1, gamma 2, 3, so on and so forth. And then you have your gamma.
So I'm trying to digest the definition of convergence here. So
yeah.
So So when you say that for sufficiently large n, are you really saying that gamma n is equivalent to gamma for little n big sufficiently large?
It's
Or is
not.
it different?
It's different because it's only like
Specific values of t,
y-
n.
yes, and also it's not for. The thing is like for every bounded b,
Right.
this n will be different.
Uh,
So like like let's say like gamma 5 and gamma are in the same path connected component for some bounded b. For the bigger one, maybe it's not true.
okay.
So that's what we're going to show here is like the idea is not that they are the same end. It's more that obviously if I look at this sequence of ends 1, 2, 3, 4, 5, it looks like it should converge. I want to intuitively say that it converges to gamma, right? It keeps going that way. And what I do is I remove bounded sets. Say I remove this set away, and I look at the remaining space. There should be, so basically I've removed a little bit from the beginning. There should still be an infinite number of ends in my sequence that lie in the same path connected component after I remove it. So I keep doing it bigger and bigger, and there are still more that go that way. Does that make intuitive sense?
Yeah.
Okay. So yeah, that's your, and well, when you want to define a topology, and you're defining it through, you're starting out by defining convergent sequences. What's the obvious thing to do? What do you do with, because you're defining limit points, right? What do you do with limit points in a topology? You make sure that, yeah, you make sure that that's how you define the closed sets, right? So then that's how you define the topology. Set U is closed, oh, sorry, closed if a sequence of ends is in U implies that the end that it converges to is in U for the sequence converging. So if my sequence is in the set, then the limit point is also in the set. Then I define that as a closed set, complement that, you get the open sets. And that's your topology. This is, everything we've defined so far is equivalent to what we talked about last time.
Is there a way to give a basis for this topology, or is it something really inherent?
Basis. I mean,
You could write that out explicit. I mean, yeah, because it does define a topology.
yeah. You could, especially because it's an equivalent definition to the last definition, you could just use the same thing, except now you have nicer properties because it's a metric space. So instead of, we had to remember we defined the basis for the last one as taking the open sets that contain like a connected component, and then you basically add the end that it contains to that open set. So you keep doing this, so you can do the same exact thing here. And then, well, that would be your basis for the compactified space, and then you mod it to get the.
So is this new topological space on end of x is it going to be a metric space?
It's going to be a metric space.
Or
There
is
is.
topological space?
It's just a topological space. Yeah, it's not. Is it a metric space? There's no. I don't see a.
No. I mean, there's no obvious way of
Yeah. Okay. Yeah.
There's coherent.
Right. And actually, I wanted to show you this just because we're going to be eventually talking about the ends as a space, but the specific topology itself is not necessary. You don't have to memorize it for the rest of the talk. Can I still go over there a little bit? Okay. So we defined our topology. Now is the tedious part. This is what I've been dreading. So if those are your initial notions, you have geodesic space, proper rays, ends, paths, path connectedness. There's equivalent stuff. I'm going to put the word quasi in front of everything, and then there's a whole bunch of notions. So there's actually, let's see, quasi-isometric embedding. There's quasi-geodesic, quasi-geodesic space, quasi-proper rays, quasi-ends, quasi-path connected components. And it gets pretty tedious, but I think I'm going to touch on a couple of these things just so that we get a clear idea of what we're doing. I could avoid this, but I think it would be a good learning moment to see why exactly we had to do this kind of weird thing. So I guess we'll start with defining a quasi. Did I spell that right? No. Isometric embedding. Okay. All right. So quasi-isometric embedding from a space to another space. Just assume metric, whatever. You know, they're both metric spaces. Is a not necessarily continuous. It's just a map, such that there exists a constant greater than 0 and another constant greater than or equal to 0, such that the distance in y. So it's like okay, maybe I should say this before I write anything down. Whenever I say quasi, I'm basically trying to define a notion that's analogous to the actual notion, but it's coarser. So if you like zoom out, squint your eyes enough, it looks like it, but it's not it.
So this is going to be something that almost preserves.
Exactly, yes, yeah.
It's going to be.
Yeah, everything when I say quasi, it's almost preserving something that the actual thing is preserving.
Can be preserved.
Yeah, exactly. So the distance is not preserved. It's bounded both from above and below by a multiplicative error and an additive error. I'm so sleep deprived.
These B's and C's, they're independent of X and XI?
They're dependent on no. Sorry, no, they're not. They're just you fix a B and a C, and you basically call it. I'll probably write this maybe. You call it a CB quasi-isometric.
Okay, but it's independent of the points.
Yes. Yeah.
Okay.
Right. I think otherwise you can make anything basically a quasi-isometry. All right, so yeah, that's our quasi-isometric embedding. Now we define a quasi-isometry. Which is a map F y such that F is it's a quasi-isometric embedding. And then also such that there exists a map going back from y to x, which is also a isometric embedding.
Is it CB quasi-isometric embedding?
It doesn't have to, because you can adjust the parameters. Like you can find like the maximum, minimum of them.
Okay, give me some different parameters.
Yeah. It's also such that the composition of the two is, well, it's not equal to the identity. Like you would assume it's finite distance from the identity. So I'll tell you what that means. Distance from the what was it? You wanted me to do this? No?
No, it was
Okay.
little d.
No, I was just messing with you, yeah. From the identity on what? Is it y? Y, and also vice versa. So G composed with F is, again, finite distance away from the identity X. And I'll define finite distance here. Our finite distance away if for all x and x prime. I think I'm reaching like the,
Yeah,
right?
You're good to this line.
Okay, last line, all right.
Last line.
For all, this is the end of this space. For all x and x prime, the distance between the outputs, so distance between phi of x and phi prime of x. Okay, then I should probably not say this, sorry. For all x, the distance between the outputs is bounded by a constant, if that makes sense.
So
It's literally a finite distance away.
yeah.
So now we've defined a quasi-isometry. The thing about quasi-isometries is that they're not necessarily continuous, they're not necessarily injective, they're not necessarily bijective. So you might be asking, why the heck are we even studying them? There's nothing nice about them. But soon enough, you'll see that if once we start talking about
So
geodesic,
in our definition of quasi-isometric embedding, we're not assuming f is injective?
no,
No? Okay.
yeah, I know embedding like
Yeah, that's a bad naming.
Yeah, I know.
Usually is injective.
I don't know why they did it. Probably just because isometric embedding, quasi. Right, but this has basically no good properties for now. Like,
Right, yeah.
don't assume anything. But soon enough, you'll see. There's things that'll fall out. All right, I'm going to erase this because, like I said, the actual way to define the topology is not that necessary right now. Not that important. It is necessary. All right, a couple more notions. Let's see. All right. It's 37 already?
It's been 27 minutes, yeah.
Okay, all right. A couple more notions.
Are we stopping at 3 or?
We could keep going, right?
Yeah, we can go.
Yeah. It's up to the audience. Like, I don't want to bore you guys to death, so whatever you want. Let's see. Isometry. Should I do? I'm going to do all of it. Yeah, whatever. Screw it. Okay. So quasi geodesic is, again, it's exactly what you think. It's a map from, well, this time it doesn't have to be a map from 0 to L. It's a geodesic, so we don't care about structure at all. Did I write? No, okay. I don't know if I should write. Yeah, okay, whatever. Yeah, such that F is a symmetric embedding. So it's the same notion, but you replace isometric embedding with quasi-isometric. And so now you know what a quasi-geodesic space will be. It's just a space where any points will be connected that way. And you have proper quasi-rays. I'm not going to, so proper is this part. So proper is this part, but I'll just write down what a quasi-ray is. Ray is, again, not assuming continuity. This doesn't assume continuity. This doesn't assume continuity. It's just a map from n infinity such that the distance from gamma, let's see, x prime is bounded above by some constant times your, some constant times, where should I write this? Under? Okay.
So that's like Lipschitz. Oh, no?
It is, it's close to. If you get rid of this, it's Lipschitz, yeah. Yeah, you just want to keep removing as much niceness as possible. You
Right.
take isometry, remove it. You have Lipschitz, remove more. Right. So, and notice that this is only bounded above, so it's not exactly like the same as the others, but it doesn't matter. The point remains. So now we have quasi-ends. Finally, there's a reason for all this tediousness, I promise. So again, two quasi-rays are equivalent if and only if for all bounded blah blah blah, blah, are this time they're quasi-path connected. In same notion, I replace my path-connected components with quasi-path connected components. So what's a quasi-path? It's what you would think it is. I'm going to erase this basically as soon as I write this, so don't worry about it. Quasi-path is a function from an interval in t of x such that, again, this time, it's only bounded above, so the distance between 2 points, bounded above by some constant. So one thing to notice is, in general, you could have, if you have a certain number of ends, you could have way little quasi-ends, just because two ends could actually just be the same quasi-end. They can, because the whole point of this construction is that, just as an example, if there's like two ends that go off like that, to be even closer, just to make the point even more geometrically intuitive, I can like use quasi-rays to jump between the two, and because they're quasi-rays, it's still allowed to do that. So you can,
So they can be in different branches. So.
but they're close enough to be the same quasi-end.
And sorry, again, what goes in the parentheses for quasi-ends?
Yeah, if and only if for all bounded B there exists a time such that after that time they're both in the same quasi.
It's the same, but it just changes it.
Yeah, exactly.
Quasi-path.
All good? Okay. Well, hopefully, because our construction relies entirely on being able to define this properly.
Actually, yeah, technically over here, you should run a absolute value of x minus x prime, right? Times b.
Oh, yes, you're right. Yes, sorry.
I know, but I meant a line, two lines above as well. There's a metric x on x prime, one more line.
One more.
Right, the right side of the inequality. Yes.
Okay.
That should be absolute value of x minus x prime now.
Which is the distance from x?
But the distance belongs to the space x, not the real line. Just the accident. Okay, yeah.
Okay. Are we okay? We happy?
All right, yeah.
Did I do anything else that you need to? No. Okay.
Yeah, that's fine.
All right. Do you want me to write a subscript for this as well? What is this? Where does this belong? Let's see. Belongs in x. Oh no, it belongs in y. Okay. All right. We're all good.
Yeah.
Okay. Okay. All right. Okay. So let's see. So we've defined quasi-ends, and in the same way as we defined our n space, we just take those the equivalence classes, and you define your quasi-n space, which we're going to denote as n cube of x, which is the quasi-ends. So now, why all this madness? Why do we do all this? Well, everything will come to light once we get into our next idea. I'm going to erase this since everything here is clear. Yeah. Okay. I've basically defined the notion twice now, so it should be clear. So, let's see, am I ready to do the? I think I am. Yeah. Okay, I think I've set it up. All right, we have our first theorem. This is basically why we did everything. Given given a quasi-isometric embedding from one quasi-geodesic metric space to another, we can induce a map. We're going to denote it as end of f from the end quasi-end space of x to the quasi-end space of y, such that the map takes an end represented by some quasi-ray and takes it to the end represented by, the quasi-ray that you get when you pass the initial one through your quasi-isometric embedding. So basically, I have my space x, space y. I have a ray. I pass it through f. So this is f. This is gamma. This is f composed of gamma. And whatever space, whatever end that goes to is what you're looking at. Our first idea is that this map is well-defined and continuous. And now you see we get our first nice property that follows out. Finally, we have something continuous. And this is only going to get better from here. So yeah, it's well-defined and continuous. The next point is that.
Okay, so let's adjust that. So
Yes.
here my definition is quasi-isometric embedding.
Mhm.
Continuity wasn't part of my definition.
No.
Right?
No.
It wasn't.
Mhm.
So this is, but the moment you define it on here, it becomes.
The moment I define, so this is the induced map that you get
Oh,
from.
this is the induced map from map.
Yeah,
That is continuous on these.
On the end space.
On the end space. Okay.
Right, right. And that's why, I mean, if you want to work this out yourself, prove that it's continuous and well-defined, you know how to create the topology, so you can do it.
The topology designed to make these things continuous.
Yes.
Okay, sure.
And it's a good thing that it all coincides with what we talked about last time. So, okay, well-defined and continuous. So, and this is another important point. If f and g are two such embeddings that are finite distance away, again, definition of finite distance away is over there, then the maps induced by them are actually, they coincide, they're the same map. So if they're finite distance away, then they take each end to the same exact other end. And this is the important point because, let's see. Okay. Then in particular, if f is a, did I already define? Yeah, I did. Okay. Is a quasi-isometry. So a stricter notion than an isometric embedding, which isn't even a real embedding, is quasi-isometry, then what do you think happens? We're very close. We already have something continuous.
Is the induced map going to be an isomorphism?
It's a homeomorphism, yeah.
It's a homeomorphism.
Yeah, because it's between spaces. Yeah.
Okay.
Then F is.
Well, I mean, what we have is we reverse compulsion. This is only a finite distance away from identity, right?
Mm-hmm, yeah.
We just said that they're the same thing, right? So basically, the induced map would be identity. Oh, so yeah, it's an isomorphism. Yeah.
It is.
Yeah.
It's like, well, but it's an isomorphism on spaces, so it's a homeomorphism.
Yeah.
A homeomorphism. F is a homie. See, I told you nice things show up. Continuity,
Right.
homies. So why did we?
I think maybe now I'm trying to guess where you're going to go next.
Okay.
Right, when we just try to describe a functor which takes us from this space to the induced n space and its isomorphisms.
Oh, we already did. Yeah, this is it. Yeah.
You're describing the functor, right?
Yes. Yes. So yeah, you have the you take the quasi-isometry, your function, and pass it to your homie end of f. Oh, sorry. So I should probably write end of f is the homie.
Yeah, n is the functor, right?
Yeah. Yeah. From your full category, subcategory of quasi-isometric metric spaces. Into
so
topologies.
with the induced map of a quasi-isometry, are these your maps you want to consider for your category, or okay.
Yes, yeah, these are the ones. We could get into the categorical notion, but this is basically there's not much like actual categorical math behind the rest of the talk. But yes, it is the end is the functor. Homie, and now you see why we had to do this whole thing. One thing is one of the reasons we had to do this is because now we've proven that n space is quasi-isometric invariant. If there's two spaces that are quasi-isometric, then the n spaces are homeomorphic. So that's the main thing, one of the main things. So in particular, the n space of x is a quasi-isometric invariant. Sorry. So we've already seen that n space of x is it's a homeomorphic invariant. But that's not enough for us because we're soon going to be talking about ends of groups. And so, and we'll see why this is important, why we need to prove that it's a quasi-isometric invariant as well. And you might be wondering, why did I do all this if I could have just said, given a geodesic space, and given these are all just ends, not quasi-ends, I could have written all this down without going through all these quasi BS, right? And the reason is this little thing right here. It's that. Even if I was working with a geodesic space, when I pass a ray, so let's say I'm working with the geodesic space, and let's say I'm actually working with proper rays, not quasi-rays. If I pass this through a quasi-isometric embedding, because the embedding itself is terrible, it holds no good properties, what you get out is not going to be a ray. So even if you're working with a nice space, when you do this construction, you need to find a way to represent your ends using something much looser than rays, right? And the way you did that is by saying, well, I don't need the entire data that's within my ray. I just need points in my ray. If you just take sample points, I can still tell you which end I'm going to, right? So that's where this idea of quasi-rays come in. But now that we've constructed it, we can completely forget about it. That's the good thing about this, because the next theorem is going to allow us to just forget about everything we just talked about and just go back to our nice little comfort spot. Just ends, good old ends. Okay, I guess it doesn't deserve to be a theorem. It's a proposition. X is he's a geode met. Then then the quasi-ends of X coincide with the ends of X. See how now we can just forget about quasi-ends. The reason we used it is so that we can pass it to this functor, make this end of f well-defined. That's the only reason that we use quasi-ends, but now we can forget it. And also it has some other nice properties too. So if X is also, in addition, proper as a space, as a topological space, so meaning closed balls are compact, then for all X in your space, for all elements in your space, every end, can be represented by a geodesic starting geodesic array starting at x. So you can pick any point in your space, and then you can find the geodesic array that represents all your n's. And that's like pretty intuitive if it's, right, you can pick if you have like a graph or something, spoiler alert, an infinite graph, so it goes off into infinity. You can pick any point, you can start at any point, and then just pick a geodesic array that goes off into infinity to define every single n. I was told that I should stop mumbling so much.
By who?
My brother.
Your brother?
Yeah, so apparently the mic isn't picking it up. So I never liked you anyways. Okay, so we have a proposition. So again, this makes it much easier to work with because what we're going to end up doing is working with geodesic metric spaces, proper geodesic metric spaces. I have very little time. Okay, let's see, what else do I want to do? We're just not getting into groups. Are you guys tired?
I'm fine. Go as long as you want.
Okay, because I don't care about YouTube because they can just pause and play whenever they want. So as long as you guys are fine. Okay. All right. So, all right. Let's get into groups now. I'll keep this. I'll erase that.
So just clarification, maybe I missed it. So n of q is an n space defined by this quasi arrays, right?
Yes.
Equivalence relation on quasi arrays, right?
Yes. Yeah.
Okay. So all right. So this induced map was for quasi n space.
Mm-hmm.
And what you're saying here is in proposition, quasi n space is still the same.
The same thing, yes. As long as you have a geodesic metric space, you don't care about the distinction. Yes. And like I keep saying, the whole reason I wanted to go through this BS is because I wanted to point out that this is the one thing that troubled us into having to define all those quasi stuff. So,
Okay.
all right, so let's see. Ends of groups, finally. Oh, wait, not finally. Okay. Okay. You have a group G. Let's start talking about how to associate with your group finitely generated. Associate your finitely generated group with a topology, a geodesic metric topology, topological space. Then we denote by K of G, the Cayley graph. The Cayley graph, or maybe I should write Cayley graph subscript S of G is your Cayley graph of G. That's generated using a generating set S. Does that make sense? So the idea is a Cayley graph is a graph that you associate with a group where you put vertices for each element in your.
So like a free group of 2 letters, right? Like this infinitely branching tree.
Yes, yeah. Isomorphic to Cantor space, yes.
Yeah.
So you put a vertex for every element in your group, and you connect 2 vertices if there's a. Yeah, but the multiplication has to be from your generating set S.
Okay.
So obviously the Cayley graph depends on your the generating set that you pick, which you can pick multiple generating sets for different groups, or for the same group. And that's where, that's another reason we had to go into proving that your n space is quasi-isometric invariant. We'll talk about it. But let's first define a metric on this space. Right. The distance, I know Abril loves subscripts. So, from G to G prime is exactly what you would think it is. It's the minimum natural numbers such that there's a set of generators, n generators, well, you have to include obviously the inverses of your generating set. You want a symmetric generating set, and you want to get rid of any redundancies, so no more identity, such that, so let's say such that G times S1, S2, dot, 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 Sn is equal to H. So what's the minimum number of steps do I have to take to get to the other element? So that's our metric. You can prove that it's a metric. The 3 axioms. But it's not quite a geodesic metric space yet. So in order to turn it into one, we're going to do a process called. Can you tell me where I can end so I can just be aware? Can I do this?
Yeah, around there.
Okay.
Something below that.
Okay. What was I going to do?
Why is it different from geometric?
So we're going to use we're going to do a process called geometric realization. So the idea of geometric realization is, in this specific case, taking a connected graph and associating with it a geodesic space. And that way, and proving that coarsely the geodesic space approximates your initial graph. Coarsely in the sense that there's a quasi-isometry between them. In general, you can take any quasi-geodesic space and approximate it using a geodesic space, but we're going to do it specifically for your graph. And I'll just give you the geometric interpretation of what happens, because the definition honestly is like not going to fit in here. So let's say you have your graph. I'll do this. Okay, so there's your vertices. You have more, obviously. What you do is you define the topology on this graph by first taking the vertices and then gluing them topologically to unit intervals. So these edges are actually just compact unit intervals from 0 to 1. And you glue them, all these disjoint copies of them. And then you argue that I can create a metric. I can expand the metric that I already have. This is the word metric. I can expand this metric to make this a geodesic space. And the way I do it is, let's say I pick this point, and I want to find, or not this point, sorry. Let's say I pick this point right here, because I want all of my points in my space to have some sort of metric, distance function. So I pick this point here, and say I pick this point here. The distance between them is exactly what you would think it is. I first take the closest element, either this one or this one, doesn't matter. I pick this element, those two are those two are group elements. So now I can find the distance between those two just by using my word metric, because they're both group elements. And then I can add this decimal plus this decimal length to that. And then now I have a metric on every point in space. Does that make sense?
But then so wait, this is a graph, right?
That's a graph.
So like it depends on how you represent your graph, right? Distance.
In terms of the generating set?
Well, you're defining a distance on all the points of the graph, right? That's the whole point.
Yes.
Because you have this additional fractional part, right? But what if I made one length arbitrarily large, right?
If you're talking about the fact that this point and this point are also connected through this path.
No, what I'm saying is that depending on how you draw your graph, your metric depends highly on how you draw.
On how you draw your graph, but you drawing your graph depends entirely on your generating set.
Right.
So if you fix your generating set, there's only one way to draw the graph.
Okay.
If you're talking about like directed versus undirected, like orientation, like the orientation of the edges, that kind of stuff, or you just mean?
Like I mean, like if I draw the vertices of a rectangle versus the vertices that are like a rhombus shape, right? One of the sides is going to be longer, right?
Yeah, these are all unit intervals.
Oh,
They're
so
all
you
length
make them
1.
all unit, okay.
Yeah, yeah. So yeah, even if it's a rhombus, yeah, I'm just going to call this 1, 1, 1, 1.
I see.
Yeah. That's So because otherwise you want the things to be consistent, right? Like if I use my distance, my word metric to find the distance between 2 points, I want it to coincide with if I just took the actual arc length, right? You did remind me though. There's one thing to note. If I'm trying to find, like I said, the distance between this point and this point, I can also travel to it using another connected path. But I find the closest, the smallest one, because that's what defines it. Right. I'm going to leave this picture. We can. This is basically it. There's nothing. You don't have to even remember it. It's the most intuitive thing. This turns our calligraph into a geodesic space, and now the hard work is finally almost done. We've actually, let's see, we've gotten our geodesic space, so all of these things just fall right out. And you can apply all these theorems to your calligraph. More specifically, I'll probably write this part down. Yeah. Okay, I'm going to erase this. The reason you wanted it to be a quasi-isometric invariant, your end space, is because calligraph on S of G is quasi-isometric to the calligraph S prime G for two S and S prime being finite generating sets, fin-gen sets. So meaning, yes, it's true that the calligraphs depend on your generating set, but they're always going to be quasi-isometric. So as long as I find something that's quasi-isometric invariant, I found something that's invariant for my group. So now we finally have an invariant, and we have a way to associate ends to a group. Let's see. So now we change this to ends of groups. What else do I want to do?
So can two different generating sets have different size?
Yeah, they can.
Okay. So it's not the one's minimal.
Yeah, there's no restrictions on the size as long as they're two finite generating sets.
So I could have chosen, for example, S is equal to the whole group.
Yeah, you can. It would be a crazy quasi-isometry, but the C and the B would be really big, but you can make it work. Let's see. Should I go into? So I think we're ready for talking about a couple important theorems. We've defined how to associate ends to a group. Last time, there's a lot of different notions of this. The last time we talked about associating ends to a topological group. That's easy because topological groups are also spaces, so you just look at the ends of that space. And then I alluded to the idea of studying a topological space, or studying a group by looking at its action on a topological space and studying the ends of that topological space. So now we're finally just directly associating a space to a group and studying the ends of that space. And we can look at some theorems that fall right out. This one is analogous to something we did last time. Half.
Is that famous half, like half iteration half?
It might be. Yeah. I'll let you know. I don't know. Okay, so Freudenthal half, we have a finitely generated group has either 0, 1, 2, or infinitely many ends. And there's a nice way to categorize most of these occurrences. So these are all the possibilities. You either have 0, 1, or 2, or infinite. The only difference between this and last time was that a path-connected topological group can't have infinitely many ends, but everything else still applies. It's either 0, 1, or 2. We can, if you want, I can show you a proof for this. I'm going to pass the ball back to you guys. Do you want to see a proof, or do you want to trust me, bro? I'll take trust me, bro, or proof. It's up to you.
I can trust for the moment.
Trust for the moment. Okay.
So is this what the thing that you were trying to get at? The big theorem that you wanted to get to?
Well, this and then I wanted to categorize all finally generated groups in terms of their ends.
Okay, well, like that was pretty obvious. Maybe it's just.
Yeah, yeah. Well, that one I'm not proving either. So
No, it's fine. But,
yeah. How much time do we got?
well, you've been talking for an hour. But
Okay.
you
Then I'll probably, okay, that's good. If I've been talking for an hour, what I'll do is I'll just write down the last theorem and we'll conclude the talk.
So,
Yeah, go ahead. All good? All right. So last theorem we'll talk about this kind of categorizes all finally generated groups into these four categories. So let's see. A finitely thin-gen group has 0 ends if and only if G is finite. One end, I'll get back to that. Two ends if and only if G is virtually Z, so which means there exists there exists a finite finite index, yeah, finite index subgroup that's isomorphic to Z. So yeah, it has to be finite index because you're trying to like virtually see, yeah. You're trying to say that it's mostly, yeah.
They have the same cardinality.
Yeah, exactly. Infinite. That's not how you spell that. Infinite ends. And I'm not going to get too into what splits over a finite group means. For those of you in the know, I guess I can write this part. It's tedious to define exactly what I'm talking about, but this just means that either two cases. G is an amalgamated product, free product of G1 free product G2 such that G1 and G2 are finitely generated. A, okay, well, A is a subgroup, but I'll just get into the more important fact that it's a non-trivial subgroup of both of these guys, both of your finally generated groups. Also, A is finite. Should I say that? Or is it finite index? Should be finite, but no, it shouldn't. What am I saying? No, okay. And also, one of the indices has to be greater than 2. So they both can't be equal to 2. This is really not the important point. I just wanted to show that you can basically categorize all finitely generated groups into these things. The other one is an HN extension. by an isomorphism between two finite subgroups of a group G, group G prime. Again, don't worry about all this. It's just that with zero, if it has zero ends, it is finite. If it has two ends, it's basically Z. It's the same cardinality as G, has a copy of it inside. Infinite ends, you can categorize it in one of these two ways. In either case, you're splitting over a finite group. And the one end case, so that's the interesting part, that there's a lot of, there's no way to actually like categorize them yet.
So, like, it's like the more ends you have, the bigger cardinality.
The more ends you have, the bigger the cardinality is. Yeah, in some ways, yeah. I mean, yeah.
So there's like something between like Z and so the group, whatever it corresponds to,
Mm-hmm.
something that's in between being finite and countable.
It's finite and countable. In between finite.
Because Z, I mean,
But in between finite and countable was.
It's probably countable still.
Right.
Still
It's definitely not finite, yeah, but it's right. I think if you have an uncountable number of elements, I think you're supposed to have infinitely many ends. Yes.
You say two ends, you just like branches?
Uh,
Versus one end where it's just like a line?
no, versus one end, which is just an array.
Oh, yeah, okay.
Yeah, a line would have two ends.
Okay, yeah, that's what I was like.
Right, yeah. So you only have one way of getting to infinity. So, and I think that's where we stop. This is good places I need to stop. Any questions?
No questions. No, if it was saying to stop, I would have asked.
We could look it up.
Yeah, maybe.
Yeah.
Freudenthal was alive in the 1930s.
Mm-hmm. Yeah.
So yeah, they should have been.
At the same time?
Yeah,
Yeah, okay. That makes sense, yeah.
Yeah.
Mm-hmm.
Well, thank you. I feel like you were kind of dumbing down the issue. What is
For myself, mostly.
impact of
The impact of knowing? Well,
applications of this?
right. Well, this is one application. I think mostly the idea it comes from specifically the ends of groups comes from a topic called geometric group theory, which is like sort of the converse of algebraic geometry. So in algebraic geometry, you study the geometry of a space using the algebraic structure you place on it. In geometric group theory, you study the algebraic structure in your group by placing a space on it and studying its geometry. And that's exactly what we did here. So an example of a geometric object is these ends, right? And what you did was you associated a space to your group and then studied the number of ends that it would have. So then you have a nice way of categorizing all your groups. So one application would be if let's say you found a group, you were like out in the wild and you found a group, and you wanted to see if it was isomorphic to another group that you had in your pocket the whole time. What you could do is compare the number of ends that it has, and if it doesn't have the same ends, then it's not isomorphic. So, that goes in general for any kind of association that you do in mathematics. If you associate one structure to another, what you want to do is use that structure to differentiate the initial structure. Say that if these structures aren't the same, then the things I'm studying from the beginning weren't the same. They weren't isomorphic.
Okay, gotcha. So they have the same ends. They're not necessarily isomorphic.
No.
But they don't have the same ends.
Yes. Yeah.
Good test.
It's a good test. Yeah. The mathematician's dream would be that you find the invariant, which is like it goes both ways. If they have the same ends, it's the same group. If they don't have, but that's almost never possible. So you settle for finding as many invariants as possible, so you can like find some way to prove what you want to prove. Anything else? Okay, let's thank the speaker. All right.